Hello everyone, this is Chao Feng from Northwest University. Now I gonna present our work, RFlens, Metasurface-Enabled Beamforming for IoT, Communication and Sensing. This work has been done with Northwest University and University of California, San Diego. Next, we will talk about our motivation. As we know, beamforming can enhance the wireless communication and sensing capabilities in a wide range of IoT applications. For example, improving the link capacity. The transmitter can focus the signal power towards the intended receiver, much desired, for battery-powered sensors such as surveillance cameras. Multi-user wireless via for education and gaming, where high-bandwidth data must be streamed to each user. Second, improving the secrecy capacity, using directional beams to reduce the risk of eavesdropping. Third, improving sensing capability. The transmitter can perform beamforming to spotlight on a desired subject, thereby reducing multipath interference. Thus, beamforming is very highly desired in our daily life. However, low-cost IoT devices are typically equipped with only one or two antennas, which cannot support beamforming. Traditional methods use many antennas in the radio end to perform beamforming, which need to tightly integrate the antennas, RF front end, and baseband hardware. They are bulky and costly, cannot match small and low-cost IoT devices. Other works such as Lava and O-Focus, while these systems can realize beamforming gains, they require a large area to deploy antennas. Their form factor is formidable. So, can we design a more area-efficient smart surface to enable beamforming capabilities? Thus, we present our work, RFlens, which can reshape and re-steer the RF signals going through Metasurface. The basic idea is that RFlens consists of many unit cells. Each unit cell acts as a 1-bit phase shifter. It can manipulate the phases of incident waves, thereby achieving beamforming. How to realize a compact Metasurface with high beamforming gain? Each unit cell should meet two requirements. First, dynamically and independently adjust the phase. Second, low transmission loss. Firstly, to design the unit cell with phase shifting capability, we used PIN diodes with same orientation on the active patch layer of each unit cell as the basic elements. When applying to different DC voltage values, the PIN diode switch to an opposite state, and thus forms the phase difference of 180 degrees. We use high phase to verify it. The result is as shown. The phase difference between two states is stable at 180 degrees on all frequency band. Secondly, optimized transmission loss, which includes transmission attenuation and reflection attenuation. For transmission attenuation, it depends on the substrate material of the unit cell. For example, Rogers Doroid RT6002 has a low transmission loss, but it is expensive. To reduce transmission attenuation, we select FB as the substrate material for balancing the cost and transmission attenuation. For reflection attenuation, it is correlated with the resonant frequency of unit cell. To reduce reflection attenuation, we build an equivalent circuit model for the unit cell to identify the key parameters that impact the resonance frequency of the unit cell, including patch lengths, patch widths, slot size, metallized via diameters, and dielectric substrate thickness. Then, we use high phase to explore the impact of the 5 parameters. The figures indicate that the impact of these different parameters on reflection attenuation. Finally, we use these parameters to adjust the unit cell we can see that the transmission efficiency exceeds -3 dB under our parameter setup across the entire from 5.15 to 5.89 GHz band. Then, how to use the designed metasurface to achieve single beam pattern. Generally, to steer the beam towards the desired direction, the phase distribution, as follows. Since an incident signal impinges on the unit cell located, it causes a phase shift. Hence, to perform beamforming, each unit cell need generate a phase compensation for aligning signal paths, as follows. Recall the unit cell only provides, to phase states 0 or pi. We perform a quantization operation of phase compensation as follows. Then, we conduct high phase simulation to analyze the radiation pattern. From the figure, we can see that different angles have different phase coding patterns, and the main beam direction of the unit cell design is well aligned with the ideal case. Thus, by configuring different phase coding patterns, we can steer the signal beam towards the desired direction. Then, how to use the designed metasurface to achieve multi-beam pattern. A straightforward approach to form multi-beam is to divide the whole metasurface into subarrays, each independently generating a single beam. But this will hurt the directionality, since each subarray only employs a subset of unit cells. We devise a beam synthesis optimization scheme. The basic idea is to synthesize a desired multi-beam pattern by iteratively adjusting the phase states of unit cells. From the figure, we can observe that, first, the beam width of the two main lobes are narrower than the geometrical method. Second, the side lobe levels are much lower than the main lobe levels, and third, the two main lobes well match the desired angles. Next, I will tell you how we imply our system. We fabricate the prototype including 256 functional unit cells, with a total surface area of 48.4 multiplies 48.4 square centimeter, and a thickness of 6.2 millimeters. To control the bias voltages for all the unit cells, we design a control circuit module consists of two Arduino Mega 2560 controllers and 3 to 7 for HC595 shift registers. Then we conduct experiments by using one USRPN to 10 software-defined radio, with a UBX40 daughterboard as the radio transceiver, a default center frequency of 5.50 GHz. To verify the effectiveness of our RFlens over the entire 5 GHz ISM frequency band, we measure the signal strength by varying the operating frequency from 5.18 GHz to 5.81 GHz with a step of 0.09 GHz. From the figure, we can see our RFlens works well at entire ISM band. To explore the performance of beam steering, we move the receiver along the semicircle from -90 degrees to 90 degrees with a step of 5 degrees. From the figure, a RFlens performs accurate beam steering, reaching up to a wide range of 120 degrees from -60 degrees to 60 degrees. We ASLO test the performance of the dual beam, including symmetric angles and asymmetric angles. We can see that our RFlens works well in both cases. To verify the metasurface robustness, we manually disable a random subset of unit cells from 0 to 256 and measure the received signal strength. The result is as shown. The white dashed line shows the reference magnitude without using a metasurface. We can see that our RFlens still achieves high gains with a few unit cells disabled. We now evaluate the performance of our RFlens in 3 different environments. We conduct extensive experiments in the laboratory, office, and anechoic chamber. Our RFlens can achieve an average improvement of 5 dB up to 9.2 dB. We demonstrate how RFlens can help improve the secrecy capacity of the low-profile IoT devices without beamforming capabilities. Specifically, the target receive end is 2 meters away from the transmit end. The eavesdropper moves on the semicircle of the transmitter with a radius of 2 meters. We can see that RFlens can reduce the risk of eavesdropping and effectively improve the secrecy capacity. To explore the wireless sensing performance under interference of RFlens, we ask the target performs the deep squat 3 times with and without metasurface. Meanwhile, an interferer locates 2 meters away from the target, walking back and forth on the line. From the figure, RFlens can effectively mitigate the interference and significantly improve the detection accuracy of target activity. To explore the wireless sensing performance under N-loss scenarios, we ask a volunteer to perform respiration behind a absorber material. From the figure, we can see that the Metasurface's beam resteering greatly enhances the reflected signal strength, thus improving the detection accuracy under the N-loss sensing scenario. To conclude, in this work, we design a reconfigurable metasurface that can effectively beamform and resteer the RF signals going through it at a small physical area. Then, we devise a beam synthesis optimization scheme to create multi-beam patterns with narrow beam width and lower side lobe level. Finally, we conduct case studies for communication and sensing applications, which show that RFlens can improve secrecy capacity and enhance the sensing performance in N-loss scenarios. So this is a brief introduction to our work. If you want to get more details, please refer to our paper later. Thank you very much for your attention,